Zoom recording. All right. Well, this was review anyway, so we're fine. But yeah, good catch. Otherwise, I would have had to record it all again. Right. So we use the properties of vector addition, and scalar multiplication to write out a vector A in terms of its components. So you have the length in the x direction times the x hat vector plus the length in the y direction times the y hat vector. And then using those tools, you can then just treat it as if it's an algebraic thing and add them together. And then you'll get the components of the combined vector. And from there, you can find the magnitude using the Pythagorean theorem. Right. So there's a little bit more to talk about with regards to unit vectors. So first, we should probably define what a unit vector is, like what it really is. So a unit vector is literally just a direction. It contains no information about the about magnitudes. It has no units. It has no length. Well, it has length 1. So it's just a direction. Basically, if you wanted to tell somebody, like, which direction do I go from my house to Nugget Market or something? If I was being, I guess, an ass, I could say, follow this unit vector. And you could do that. You could specify some system of coordinates. I would tell you what the unit vector is, and then you could just go in that direction. But it doesn't tell you how far away it is, right? So the thing that does contain information about the components of your vectors, sorry, what tells you information about the lengths of your vectors are the components. So, and as you can see up here, these numbers, ax, ay, those are those components. So there are some conventions with regards to unit vectors that I will give you. So instead of calling the unit vector x hat, we actually have a different name for it for a reason unknown to me. We call it I hat. So I replaced the dot on the I with a hat. Again, just convention. Similarly, the y unit vector has a different name. It's j hat. And then the z unit vector, if we're working in 3-dimensional space, is k hat. And you may have actually seen these in your calculus classes, depending on where you are. Just going to pause to answer a question. If you have a vector a and b, to find the magnitude of a, do you use the component of a of only a in the Pythagorean theorem? Yes. So that's a good point. So the magnitude of a is just the square root of a in the x component of a and the y component of a, quantity squared under the square root. So we never really write I with an arrow. I mean, I guess you could say it's the same thing, but I've never actually seen anybody use that notation. So take that to mean what you will, I suppose. Anyway, so now that we have unit vectors defined and described, and now we actually have tools to talk about vectors in terms of their components and their directions, we can start talking about multiplication of vectors. So let's talk about that. Try not to have a dash. This whole arrow business, I mean, you can do whatever you want as long as people know what you're talking about. But, just stick with the convention if you can. As for using x hat and y hat, honestly, I actually use those pretty frequently. But for the sake of consistency with this course and with 9b and 9c, I would suggest using I, j, and k. If only because that's how it's going to be taught, and it'll just make it easier for you. But x hat, y hat, z hat, as long as you know what you're talking about, it's fine. Right. Let's talk about vector multiplication. So you cannot just multiply vector components. So there's a good reason for why you can't just multiply the components. One of the reasons is that then your answer kind of depends on your coordinate system, and generally we don't want that to be the case because you could have chosen a different coordinate system, like rotated 30 degrees or something. But for much deeper reasons and much more formal reasons, you can't. That's just not allowed. It's not a useful feature of vectors. On the other hand, there are 2 unique ways to multiply vectors in 3 dimensions. Now, I say in 3 dimensions. So in any number of dimensions, if you're in 2D or even one-dimensional vectors, or maybe even higher, 4D, 5D, 6D, whatever, there's always at least one way that you can multiply vectors. And that's the first way that we're going to talk about. The second way, for some, well, for good reasons, but reasons over your head, presumably, there's only 2 unique ways in 3 and 7 dimensions. If you're interested, you can Google it. I'm not going to get into that. So before I actually introduce what the ways, or what this first unique way to multiply vectors is, perhaps it's useful to actually justify why we might want to multiply vectors. So one reason would be, let's say that we want to find the effect of a force applied on an object where the object is sliding along a path not parallel to the direction you're pushing. So the picture to have in your mind here is, let's say that you, a person, are pushing on a block downwards and to the right, but the block can only slide to the right. So how would you figure out the effect on that block? Like how much of your force actually contributed, right? And actually, the language that we use here is, in fact, if you want to compute the work done, i.e. the amount of energy you put in to moving the block a certain distance, and you applied a force, both of which are vectors, then this method of multiplication will get you the work done. So let me get into the weeds on this a little bit. So let's say that this is some angle theta, just for example. Right, so say you wanted to actually compute that. Well, if you were pushing in the direction that it was moving, like if theta was just 0, if you're just pushing directly towards the block, then you could just multiply the magnitudes of those vectors and you'd be done, right? Because there's no directional information. But you can imagine that if you're pushing straight down on the block, it's not going to take any energy because it's not going to move anywhere. And so you can see, hopefully, that the amount of energy that you're going to use in pushing the block from, say, point A to point B will depend on what angle you're pushing it at. If you push it straight down, it's 0. If you push it in the direction of motion, then it's just the product of the force and the distance. But there's got to be some middle ground, right? So this first method of multiplying vectors is basically the answer to how to actually do that calculation. So to capture this whole phenomenon of some of the force being wasted, i.e. the force not being applied in the direction of motion, I have to introduce another concept. So I'm going to introduce this concept of projection. Of one vector onto another. So it's the definition, what I'm talking about here, kind of is as it sounds. You can think about it as, projection as the length of one vector casting a shadow onto the other vector. So what I mean by that is, well, I can draw a picture for you, actually. So if you have a vector, say that, let me draw a better vector, say that vector, and you want to ask for its projection along some other vector, say this vector, well, the resulting effect would be basically what you would get is if you put, a lamp there and you projected it down. So the resulting length of the projection would be this length here. This is the, maybe you have some angled here, theta. This is the projection. So it's basically the projection of one vector in the direction of another vector is basically how much of your first vector, how much of your first vector points in the direction of your second vector. So the way we use projection is we just say, look, the part of the force in this example that actually does work, and we'll talk about work and force later, the part of the force that actually does work is the part that's in the same direction that it's moving. And so if we can figure out a way to find the projection of the force vector, and multiply it by the magnitude of the distance vector, then we get our answer. Projection of, well, I'll write out some formulas in a minute. So this is what we mean when we say multiplication. So the first unique way is multiply the projection of one vector onto another by the magnitude of the second vector. Yes, this is closely related to one of the homework problems. There's the notation that we use for this multiplication is a central dot. So if we have a vector A and we dot it with a vector B, that is equal to the projection of A onto B. Remember, the projection is not a vector, it's just the length of the vector that is projected, times the magnitude of B. And we know how to calculate the magnitude of B. We know how to calculate the projection of A. Well, we will in a minute. And so this is a unique way of multiplying two vectors. Now, importantly, actually, let me just keep going and I'll get to the important note in a minute. So you can actually solve this geometrically just by using the picture that I showed above. If you know the angle theta, for example, between two vectors, then you can find the projection of A onto B. And so we get another formula, which you will use significantly more often than the formula above. You get A, and we often say A dot B, because there's a dot in the middle. This is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. And so when I say the cosine of the angle between them, I'm referring to specifically that angle. It's the angle that you go from one vector to the other vector. It does not give a new vector. Yeah, and actually, that's exactly where I was going with this. This is known as the scalar product or the dot product. I will try to avoid the language scalar product because often that's used to also denote multiplying a vector by a scalar. But yeah, this is the dot product. This is that well-famous dot product. And so I will just say regularly A dot B. And with that, I mean, take the dot product of A and B, and that spits out a number, right? Or a scalar, because the magnitude of A is a scalar, the magnitude of B is also a scalar, and the cosine of an angle is a scalar. So if you just multiply three scalars together, you get another scalar. So this is probably the most important features of vectors in general. Actually, all vectors have this dot product thing. And this is well defined in any number of dimensions. In fact, the dot product has a few properties that are useful to talk about. And these are just things that either you've seen already, hopefully, or you should just internalize because we're going to be using them a lot. So the first property is that a vector dotted with another vector is the same as the second vector dotted with the first vector, i.e., it is commutative. It doesn't matter what order you do them in, just like normal multiplication. Second property, a vector dotted into itself is just the magnitude of the vector squared. Now, there's some notation that I will use pretty frequently. It's actually an abusive notation, but often, if A is a vector, then what I mean by A squared, what I mean by that is that this is A dot A. Because this A squared couldn't mean anything besides the dot product of A with itself. So if I write A squared or R squared, what that means is take the vector and square it. Sometimes you'll have to determine from context whether or not the thing I was squaring was initially a vector or not, but usually you'll know. And if you don't, feel free to ask. By the way, this property is relatively easy to prove. Just use this geometric result. you get that the angle between a vector and itself is 0, and the cosine of 0 is 1, and you're left with just the square of the magnitude. Right, some more properties. These are properties about the unit vectors. I hat dotted into itself, well, we can figure this out. The magnitude of I hat, the unit vector, is 1, and the angle between the unit vector and itself is also is 0, so this is just 1. Similarly, I hat dotted into j hat is 0, because the angle between I and j is 90 degrees. Question, why is a an absolute value? So often you'll see this written. That just means the magnitude of a, which, yes, is always positive, but it's just another use of the notation. These are not absolute value signs. Good question, though. Right, so I dot j is 0 because your I hat points this way, your j hat points perpendicular to it, and so the cosine of 90 degrees is 0. So when you multiply them together, you get a cosine of 90 degrees, and so you get 0. Similarly, I hat dot k hat is 0, and we can follow this through. J hat dot j hat is 1, j hat dot k hat is 0, and k hat dot k hat is 1. So these are just relationships between the unit vectors, which are all very useful to have. Also, final useful property is that the dot product distributes over addition. So just like normal multiplication, just like how normal multiplication distributes over addition, in fact, that's secretly because normal multiplication is a dot product in a one-dimensional vector space, but throw that aside. Just like normal multiplication, the dot product distributes over addition, meaning if I have a dotted into, say, b plus c, that is a dot b plus a dot c. That's all I mean. So the dot product is particularly useful because we can use it to extract components of a vector. So let's say, as an example, that the vector a is ax in the x, or in, sorry, you'll catch me doing that a lot, ax in the I direction, plus, that's not that, plus ay in the j hat direction, plus az in the k hat direction. Then it's relatively easy to show that a vector dotted into the I hat unit vector is, well, we can work this out. It's ax I hat plus ay j hat plus az k hat dotted into I hat. Now we know that the dot product distributes over addition. And we know, so this is just ax I hat dot I hat plus ay j hat dot I hat plus az k hat dot I hat. And we know that the order doesn't matter, so j hat dot I hat is the same thing as I hat dot j hat. Same with k hat and I hat. So both of these terms vanish. We know that the unit vector I dotted with itself is 1, so this just tells you the magnitude of the component of the vector a in the x direction. Similarly, if you wanted to find the magnitude of, or the component of the vector a in the z direction, you would just dot it with k hat. In general, if you want to find the magnitude of a vector in some direction, you can dot it with a unit vector pointing in the direction that you want. By the way, not all unit vectors are I, j, or k. There are other unit vectors too. These are just the standard ones. Sometimes you might want a unit vector that points up and to the right, right? And so that would be that unit vector would be I hat divided by square root 2 plus j hat divided by square root 2. And you can check that that has a magnitude of 1 and it points in the direction you want. And so it would represent a unit vector just in a different direction. Right. So similarly, if we want to calculate a dot b, that's also fairly easy. So let's assume that a and b are both two-dimensional vectors now, just because I don't want to have to write out like 6 terms. So let's say that a is ax I hat plus ay j hat, b is bx I hat plus by j hat. Then a dot b is just the dot product of these vectors, right? So it's, I don't have to copy. It's ax I hat plus ay j hat dot ex I hat plus by j hat. And then you just use your handy dandy FOIL, first, outer, inner, last, and you'll get an expression. It turns out that the cross terms, the terms where you multiply ax and by, and the terms when you multiply ay and bx, those both vanish because I dot j is 0. And so you're just left with the terms that are I dot I and j dot j. So you get ax bx plus ay by, and I dot I and j dot j are both 1. And so you're left with this result as your answer for the dot product of two vectors. That's a good question, Priyanshi. So I would prefer it if you don't use that notation, if only because that notation is already overloaded, meaning it's used in other situations where there really isn't an alternative. So very much please do use the standard IJK. If you do have to write a vector as a matrix, please stick to column vectors and row vectors, and not the angle brackets. Please avoid those. I mean, like, it doesn't really matter. Like, it's just a notation thing. I don't care. But just for the sake of consistency, try to stick with just either curly brackets, not curly brackets, round brackets, or the IJK notation. Right. Okay. So now, so that's the first set of well, that's the first type of vector product that you can get. There's another, though, which is pretty much unique to 3 dimensions. I mean, it also shows up in 7 dimensions, but again, ignore that. The second type of product is called the vector product, also often called the cross product. So this is the second unique way to multiply vectors in 3 dimensions. And unlike the scalar product, or unlike the dot product, the vector product, or the cross product, returns not a scalar, but another vector. So if you take 2 vectors in and you cross them, you get another vector out. So just like how the dot product depended on the parallel part of a vector and another vector, i.e. it depends on what part of the first vector is parallel to the second vector, we could form another type of vector that depends on the perpendicular part. So I will draw what I mean by that in a minute. So let's say you have a vector A and a vector B. And by the way, I'm just putting their tails together because you're allowed to do that. So the dot product would have information about the length of A in the B direction, but that's not what the cross product does. Instead, oh no. Instead, the cross product cares about this distance here, the perpendicular distance that A is away from B, in a sense. That distance is just the magnitude of A times sine of theta. You can check that using geometry or trigonometry. And so you might just say that if you wanted to find the magnitude of the cross product of 2 vectors, you would just multiply the magnitude of A times the magnitude of B times sine theta, and you'd be correct. But we have to go a little bit deeper before we use that as our definition, because that doesn't tell us what direction the cross product is in. So unfortunately, in 3 dimensions, when I say perpendicular, that could mean several different things, right? You could have 2 vectors that are perpendicular to each other, and a third vector that's perpendicular to those other 2, right? There are multiple directions that a vector could be perpendicular to another in, is what I'm getting at. For example, the I hat vector is perp to j hat, but the k hat vector is also perp to j hat. So how would you distinguish between two vectors? How how would you distinguish between two vectors that you'd want to take the cross product of if one is in the I direction and one is in the K direction? So Christine, to answer your question, this A sine theta, that gives the magnitude, or that gives the component of A that's perpendicular to B, is what it boils down to. And I'll get into how that relates to the cross product in a minute. But basically, just like how the component of A in the direction of B was a sine theta, or sorry, was a cosine theta, the direction of A or the component of A perpendicular to B is a sine theta. It's just a perpendicular parallel thing. Right. So the fact that you can have multiple vectors that are both parallel to the same vector, that extra information that is contained in a vector in a vector's direction is encapsulated by the direction of the resulting product vector. So first, let's talk magnitudes. So the magnitude of this vector product is the area of the parallelogram swept out by the two vectors. Now, that's not particularly useful in physics, but it's good to wrap your head around. So if we have a vector A and a vector B, what we do, if we want to find the magnitude, is we transpose B up here, transpose A over here, so now we formed a parallelogram. The area of this parallelogram is equal to the magnitude of the cross product, or the vector product. They're the same thing. So you can work out geometrically what that area is. That area works out to be the magnitude of A times the magnitude of B times the sine of the angle between them. So this angle here is theta. The notation, by the way, is just the standard x for multiplication. So that means that from now on, you're not allowed to use x for multiplication of things. Otherwise, they'll think you're taking a cross product. And the x is also sometimes referred to as a cross, hence the name cross product. Right, so for any vector, and I told you the cross product spits out a vector. For any vector, you need to know the magnitude, but you also need to know the direction, right? So how is the direction encapsulated by this parallelogram? So the direction of A cross B points in the direction that is perpendicular. By the way, I'm going to draw a different picture here. Let me actually fix this picture. Let's make that one B and that one a dotted B. It does matter, and I'll explain why in a minute. So if you have a vector A and a vector B, then the circulation to get back to where you started has an orientation. So if you go from, so you start off with A, you draw your vector arrow A, then you cross with it B, you draw your vector arrow B attached to A as if you were going to add them. Then you can complete this parallelogram by making it go in a circle, circulate. The direction of that circulation depends on which one came first, A or B, but importantly, the direction of A cross B is, well, okay. I'm going to introduce something called the right-hand rule. The direction of A cross B is take your hand, your right hand. I hope that this looks like my right hand to you guys, but it's my right hand to me. Take your right hand, curl your hand in the direction of the circulation, and your thumb points in the direction of the vector A cross B. So in this case, I would take my hand, curl it in the direction of A cross B, and my thumb would point into the piece of paper. So in this case, the direction of A cross B is pointing into the paper, or into the screen for you guys. So this is that right-hand rule that you may have heard so much about, and I will describe in more detail what that is. So just to summarize again, curl hand, it has to be the right hand, importantly, otherwise you get the wrong answer. Right hand from A to B, or in direction of circulation. And then the thumb points in the direction of the resulting vector. Now, I haven't checked. Hopefully everybody's thumb points in the same direction that I do, that mine does. If your thumb is on the other side, let me know, and you might have to use a different rule. But I'll assume that everybody has standard human anatomy for now. Right, so again, I started off with two vectors that are that look like they're just 2D, but the cross product of those two vectors spits out a third vector that points into the third dimension, right? Meaning that you cannot, it doesn't even make sense to take two vectors and cross them if they're not three-dimensional. They have to live in a three-dimensional world, because otherwise their cross product would point in some direction that's not in that universe, right? So it has to be a three-dimensional thing. Now, there is I'll give you some properties. So by the way, hopefully you now understand how to find the magnitude and how to find the direction. You find the magnitude by multiplying the product of their magnitudes and sine theta. You find their direction by using the right-hand rule. That's enough to specify a vector, right? A vector is just a magnitude and a direction. So if you have both those, you're done. But it's useful to know some properties of the cross product so that you can handle them with components and deal with it algebraically instead of geometrically. So I'm going to give you some more properties. So first property, a vector crossed with itself has magnitude 0. Why is that? Well, a vector crossed with any other vector, including itself, is the product of their magnitudes times the sine of the angle between them. But the angle between two vectors, or two vectors that are the same vector, is 0. And the sine of 0 is just 0. 0 degrees, 0 radians, whatever. We can also talk about the cross product of unit vectors. I hat cross j hat. Well, we can use our right-hand rule. We have I hat, j hat. So then our right-hand rule would be out of the board. And in the standard coordinate system, where you have x, y, and then z comes out of the board, that would be k hat. And you can repeat this process for all of the unit vectors. J hat cross k hat is I hat, and k hat cross I hat is j hat. By the way, note that the order here matters. The reason for this is that A cross B is equal to the negative of B cross A. Right? The order here actually does matter. And the reason for that should be fairly obvious, right? If I had done this, this circulation business in the opposite order, if I had put the tail of A on the head of B, it would have circulated in the opposite direction. And by the right-hand rule, that would give you a vector that points in the other direction, hence multiplication by a negative sign. So that's really important, and people do tend to mess that up frequently. So just keep that in the back of your head at all times, that whenever you're dealing with cross products, the order does matter. For example, j hat cross I hat, that's a k, j hat cross I hat is negative k hat, whereas I hat cross j hat was regular k hat. Yeah, so positive k hat, assuming that you're using the standard coordinate system where x goes to the right and y goes up, then yes, k hat comes out of the piece of paper. That's actually what's known as a right-handed coordinate system, meaning if you take the cross product of the x direction and the y direction, you get the z direction using the right-hand rule. If you wanted to use a left-handed coordinate system, you would say the cross product of x and y gives you the z direction using the left-hand rule. But we just stick with the convention. We choose the right-hand rule, and that's what we stick with. So on exams, for example, especially when dealing with cross products, you will often want, I'll get to that in a minute. On exams, when you're doing cross products, if you're a right-handed writer, and you're writing things on your piece of paper, make sure not to be writing things while you are doing cross products with your hand, or the right-hand rule with your hand, because you will end up using your left hand and you'll get the wrong answer. I've seen students do this before. You really don't want to make that easy mistake. Right. So what we want to do now is, using these properties, we can actually establish in components what it means to take the cross product of two vectors. So this is answering Cherry's question. Typically, the direction of a vector is represented by, or typically we will just represent the cross product of two vectors just by components and unit vectors, right? We will write the cross product of this is this thing times I hat plus this thing times j hat plus this thing times k hat. And so instead of separating the component or the magnitude from the direction, which you could do, but instead of separating that, we're just going to combine them into just component notation. Oh, okay. Ryan, good question. Yeah, so yes, 0 in the I hat direction is the same thing as just or to rephrase, 5 in the I hat direction is the same thing as 5 in the I hat direction plus 0 in the j hat direction plus 0 in the k hat direction. You guys know that 0 times anything is 0, so you can just drop those terms if you want. And I would very much suggest it, because otherwise your papers will get very cluttered. But good question, Ryan. Thank you. Units do matter for dot products and cross products. In fact, units multiply. And I will get to that. Actually, let me finish covering this business of how to multiply cross products for vectors. And then I'll talk about units for a minute. And Seal, I hope I'm pronouncing your name right. I will answer that question in just a minute as well. So first, let's talk about what the cross product of these two vectors are. So it's ax in the I hat direction plus ay in the j hat direction. By the way, I'm again going to assume these are vectors just in the xy direction. You could do this with x, y, and z directions, but there'd be a lot of terms, and I don't want to write all of them. And we have bx in the I hat direction plus by in the j hat direction. So just like the dot product, the cross product distributes over addition, but you have to keep track of the order. So we have ax, so I'm just going to FOIL this, ax times bx, I hat cross I hat, plus ay times j hat, sorry, ay times bx, j hat cross I hat, plus ax times by, I hat cross j hat, plus ay times by, j hat cross j hat. Right? Does everyone see what I did there? So this is the first term. This is the, oh, I guess I didn't do first, outer, inner, last. I did first, I did first, inner, outer, last. So sue me. I did FIAL, not FOIL. So this is the first term, this is the inner term, this is the outer term, and that's the last term. So because it distributes, it precisely the same thing happens as you would normally do for multiplication. Right, so now we can use our properties to figure out what each of these things are. I hat cross itself is 0, right? That was the rule. Any vector cross itself is 0. Similarly, j hat cross itself is 0. We also know that j hat cross I hat is negative k hat. That's from our properties and the fact that you can rearrange, you can reorder cross products by adding a negative sign. And I hat cross j hat is just regular k hat. So what we're left with is ax by in the minus ay bx in the k hat direction. So what you can see here is that the magnitude would just be this quantity here, that value, and the direction would be into the board, or sorry, out of the sheet of paper, out of the screen. And the reason for that is that a and b are both in the xy plane. So when you use the right-hand rule, it has to point either into or out of the board, depending on their orientation in the plane. And that will be completely determined by whether ax times by is larger or smaller than ay times bx. That will tell you whether or not this is positive. This points into or out of the board. Right. So the dot product is particularly useful when it comes to multidimensional, and that's not scary, like two-dimensional or three-dimensional force problems. So you might have a force, which is a vector, that points in some amount in the x direction, plus some amount in the some amount in the I direction plus some amount in the J direction plus some amount in the K direction. And if you want to find the, let's say the example I used before, if you wanted to find, Ankit, I'll answer that in a minute. If you wanted to find the work done, turns out that the work, at least in very simple cases, is just the dot product of a vector, of a force vector and a displacement vector, which is just basically a vector that goes from point A to point B. So then you would take the dot product, and that would give you a scalar, and that would have units of joules. So the cross product shows up later. I'm not going to go into details here because it's involved a lot. In particular, it'll show up all over the place in 9C. But it does show up in this course too, especially when we're talking about torque. Basically, things that involve rotation will use the cross product extensively. So if you were talking about the amount of torque applied by a force, then you would use the cross product to find that. Units. So just like how if you were to multiply two numbers, let's say, or two numbers with units, say 10 meters times 5 hertz, which are inverse seconds, that would give you 10 meters per second. Just like regular multiplication, the units of cross products and dot products also just multiply. So if one vector, let's say if the vector A is, I don't know, 10 meters per second squared in the j hat direction, and the vector B is, I don't know, 3 kilograms, doesn't have a direction, let's say 3 meters in the j hat direction, plus 5 meters in the k hat direction, well, you could just take the dot product of these things and you would get 30 meters squared per second squared, and then j dot j is 1, so those terms vanish, and then j dot k is 0. So this would just be 30 meters squared per second squared. And the point is the units just multiply. A point that I didn't make and that I should make is that you have to make sure that when you have a vector, the components all have the same units, right? I couldn't have had 3 meters in the j hat direction plus 5 meters per second in the k hat direction. That's not a sensible thing to do. Meaning you cannot add vectors that have different units, because like, what would that even mean? Like, what does it mean to have 5 meters per second to 6 meters, right? Those are not, it's a nonsense question. Similarly, for the cross product, a cross B, that would also have, it would be a number in meters squared per second squared in some direction. And I didn't work this out, but it would have units of meters squared per second squared as well. So to answer Ismar's question, does that mean that we can dot and cross velocity and acceleration vectors? Yes, you could dot and cross those. Whether or not those are meaningful is a different question, but yes, you can do those. The direct, so keel maybe? I don't know what you're referring to. I'm trying to scroll up so that I can see. Oh, right. So remember that you were asking about the what the actual meaning is. So the direction of the vector is encapsulated by its components and the unit vectors. So remember, a dot product, j dotted into k is 0, so you can ignore the k part. And j cross k is I hat, you're right. So if I had wanted to do this, it would have been 50 meters squared per second squared in the I hat direction. Meters squared per second squared is just some unit. It doesn't mean a whole lot in this context. It's just squared velocity. I was just giving it as an example. Yeah, the k hat can distribute into the vector components. It is like that j cross I is just negative k. It just means k, or it just means a vector pointing in the opposite direction of the k hat vector. Right. When you say, can we use unit vector k when we can calculate a dot b? I don't understand what you're asking. In this example, you don't have to use the unit vector k. Well, I mean, you would have to. Let me back up a little bit. This is j dot j. plus 50 meters per second, or meters squared per second squared, j dot k. And so we know that j dot j is 1, and j dot k is 0. That's just from the definitions of the vector, of the unit vectors and the dot product. Right. These are good questions. No, so you can't just multiply components directly. For example, I could, if this, the a dot b is not 10 times 3 plus 5 meters squared per second squared. That's what I was getting at. You can't just multiply it straight across. The dot product is a very special way to multiply components that will be that will give a meaningful answer. The dot product says multiply the x component by the of one vector by the x component of the second vector, and then add to that the product of the y components, and then add to that the product of the z components. So that is a very specific way to do multiplication. You can't just multiply them all together, for example. And yes, Raul, yes, you can use the determinant matrices to compute the cross product. If my screen would let me scroll, that would be ideal. There it is. You guys may have seen this business before, where you have I, j, and k. You have ax, ay, az, bx, by, bz. If you compute the determinant of this, that is just the cross product. Yes, that's true. But really, all that is that's just a means of computing using these components. A cross product of vectors in 2 dimensions will go into the 3rd dimension always, yes, unless the cross product is 0, i.e. if the 2 vectors are parallel. All right, so that is us out of time. Unfortunately, we didn't get as far as I would have liked, but that's okay. We'll go a little bit faster next time, and I can answer more questions in office hours. So I'm going to stop the recording here, and I will continue to answer some questions.